Now, a very special situation arises in the growth dataset, the orthodontic growth dataset. And why is that? Well, you remember that we have the 1964 data, which were complete. So then Little and Rubin analyzed the data in 1987 after removal of 9 children. Recall, 5 boys, 4 girls lost their measurement at the age of 10. However, we do have the missing data available here, and that's one of the very few cases, because after all, it's missingness that is artificial, that is textbook, that is only laboratory or synthetic. It's not a real example in that sense. The data are real, but the missingness was used for illustration only. So let's look at it and try a few things. For example, you could say let missingness at time 10, at measurement 10, depend on the outcome vector, but in a very specific way. Let's try one by one the first or the second or the third or the fourth measurement. There's a distinction between 1, 3, and 4, because 1, 3, and 4 would correspond to missing at random, whereas number 2 would correspond to missing not at random. Why is that? Well, indeed, the second measurement, if you make missingness of the second measurement depend on the second measurement, it's potentially not there. So that would correspond to a missing not at random mechanism, if it's only that. And what we see is the 2 neighbors are most important. Y1 is very significant when it comes to predicting missingness at the second measurement, and Y3 still has a lot of information. Is it possible, therefore, that Little and Rubin started with the first measurement to create missingness at the second occasion? Well, the answer is yes, of course, but why would then Y3 have an impact? They may not have used it. No, that's true. But because Y1 and Y3 are highly correlated with each other, it's growth measurements with very high intra-child correlation anyway, it's a natural effect. It's kind of a spillover effect of the dependence on Y1 that also Y3 is significant. Okay, now we could leave it at that and say, okay, they used the first measurement. We can even estimate the coefficient. That's not done here. But we could also say, wait a minute, there are 5 boys removed and 4 girls. So gender. Would gender have an impact? Yeah, but gender is a covariate. True, but maybe that's what plays a role. And if you fit a logistic regression where you have a dependence of missingness on the first measurement and on the gender, so you fit separate models for boys and for girls, what you find is this very weird degenerate model. There is, in logistic regression terms, complete separation in the parameter space. The zeros and the ones, so the ones that stay and the ones that don't stay, within the boys and within the girls are fully separated. The way to interpret that is, how can it be, by the way? Well, by taking limits, by looking at limiting values, you see that the overall magnitude is infinity, but there is still a finite coefficient sitting there. The way to think about that is, what does it mean when you multiply 22 minus y with infinity? It means that the sign flips. 22 minus y says, at 22, I'm on the fence. So 0 times infinity, that would essentially correspond here to 50-50. But if you're above 22, that value is negative, and therefore minus infinity, a logit minus infinity corresponds to probability 0. So values, boys with values at the first time greater than 22, they stay. Smaller than 22, they go. And among the 2 children that have exactly 22, one stays, one doesn't. And that's explaining what we see. And for girls, the cutoff is at 20.7.5. So there we know it's a sure decision. Why? The values are recorded, and you don't see that unless you look at the data, but the values are recorded up to the half. They rounded to the nearest half. So you can have 19, 19.5, 20, 20.5, 21, but not 20.75. So if you're above 20.75, you stay. If you're below, you go. And that's giving us a very important message. The previous mechanism actually captures quite, this model is a very typical pragmatic model. This is what may happen in practice. We may end up with a model like this and say, okay, there is very high predictive power in missingness coming from the first measurement, full stop. Not perfect, no. If you would have had the missing data like you do here, you could still refine it and say, hey, if you look at boys and girls, we come up with a perfect model. And that's a logistic regression that no longer shows an S-shape, but rather a degenerate S-shape, which is technically the Heaviside step function with the deltas Dirac density function, etc. So it's a degenerate logistic regression, frankly, which gives therefore a perfect prediction to missingness. You cannot do better than that. The question is it right? Even that we are not sure of now. Not even with the perfect prediction, no, because you can have, it's technically possible, to have two different stories, both of which show a perfect fit, but that are different from each other. You would not know what has happened in reality without the missing data available, unless you talk to Little and Rubin. And doing that shows that it's exactly this. So we're sure about this mechanism, ultimately, because I think we did a good modeling job here, and then we verified it with the people who were responsible for creating the missingness. All of that is in a real example not possible, which means that we have to resort then to sensitivity analysis and consider a variety of plausible scenarios.